microphone is not with me today. So, but you can always go back to the permanent lectures. They're very thorough and the audio is very clear there. Okay. Last time we finished off with a alien fluid, and we wanted to study the motion of that fluid. And we concluded that we can apply the great conservation laws to that fluid and really to anything that exists on Earth that is subject to forces and displacements. You just apply even not necessarily just forces and displacements, but the greatest law ever to be conceptualized is the law of conservation. And if you think about it, that's an amazing realization. It's an amazing human feat to think about conservation. Last time we said to study fluid mechanics, fluids, you want to apply conservation of mass. And what was the formula that we concluded, or the governing equation we concluded for that last time? Was d by dt of the mass equals 0. Now, we said something that was very specific about all of these conservation laws is that they apply to a system, which is a unique collection of fluid particles that moves around in space that's always identifiably unique. So if you have a fluid flowing, remember there used to be a black marker over there. And your marker is empty, throw it away. Otherwise, you get very empty markers for you for the rest of the life. Okay. Not very good. Okay. And so we said that a system would essentially be just an arbitrary collection of fluid elements, fluid molecules. We're going to call that our system. Okay. And all of the laws we discussed last time, they apply to a system. Okay. As the system moves, it's moving from here. Let's say it moves over here. What the conservation law, the conservation of mass is saying is that mass, if it's at T0 here, T1 over here, the mass is constant or does not change. Okay. The other law we looked at was conservation of momentum, or Newton's second law, where we said d mv by dt is equal to summation of forces. This is all system. Okay? And finally, conservation of energy. Conservation of energy said that dE by dt system is dQ by dt minus dW by dt, also for system and for the system. Okay? Does anyone want to challenge these equations, challenge these statements? Set. It's good. Okay. We are in agreement, so we can proceed forward. We also said last time that this formulation is problematic because to be able to, it's one thing to track a planet or 3 planets or 15 planets or a bunch of stars in a galaxy using this formulation, right? Versus trying to track everything inside a fluid, which is made up of hundreds of millions of these little systems, right? What we would rather have is say, this is really hard to do. What I would like to see is at every every point in a fluid, it would be great to just say, at that point, the velocity is such, let's say, U1 at that point, density is ρ1. At this point, its velocity is U2 and density is ρ2. Pressure, let's say, is P1, pressure is P2. Same thing over here, U3, P3, ρ3, okay, and so on and so forth. And the idea is that any system or any particle in any system that passes through one of those points, it's immediately going to inherit the properties or the values, the quantities at that point. Okay, so imagine you are walking on a conveyor, you are on a conveyor belt, and somehow that conveyor belt has like variable speed at different points, right? You are going to immediately inherit the speed of the conveyor belt at a certain particular point, okay? Or let's say, there are temperatures at different locations in space. Any fluid moving or anything moving in that space is going to immediately feel that temperature, that pressure, that velocity, and as such. In such a description, which is called this description is called the Lagrangian, and this description is called Eulerian. In the Eulerian description, our objective is to forget about the system, rather focus on space and time. And at every point in space and time, our objective is to find all the relevant properties for fluids: velocity, pressure, temperature, and density. Okay? Once you identify those, then you can immediately say any molecule, any fluid element, any fluid system, any fluid particle that goes through that point will immediately, instantaneously inherit the properties of that point. So now we've switched our perspective from following a system to just fixing the geometry, in other words, and trying to find the flow at every point, trying to find the properties at every point. What that means is we need to figure out a way to convert these time derivatives, okay, into something that has to do with space. So these time derivatives, they don't have space in them, right? Because for a system, there's no concept of space. It's just moving, there's no, space doesn't matter to it. The only change that a system feels is a change in time. Even if the system's temperature changes, it doesn't matter where in space it is for the system, it's only change over time. That's why you only sign these stuff. Okay? Now, when we do that translation, we're gonna try to relate it to space. Okay? This translation from the Lagrangian to the Eulerian, and what I'm teaching here is a little bit unconventional in the sense of how graduate fluid mechanics is taught, but I think it kind of gives a clean perspective of, like right here, the equations of motion. It's just the standard equations you learned in high school and early undergrad. It's just simple, basic conservation laws that you've studied for your entire life. The only thing we're going to do here is move from a Lagrangian perspective to an Eulerian perspective. So if I teach you that approach, okay, it's called the RTT. If I teach you that approach, then you will be able to translate any equation from developed for a system to an Eulerian formulation. RTT stands for Reynolds Transport Theorem. It is the hallmark of engineering science, fluid mechanics, heat transfer, transport systems, really. The Reynolds Transport Theorem. You should have heard of it in your undergrad, have you? Yeah. Okay. Did you understand it in undergrad? Did you know that what purpose it accomplished? I didn't, because it was the first time I was exposed to it. And, I had a great teacher, but still he had a hard time explaining things because, we are all growing in maturity in science. We had different gaps, etc. So that's why I'm revisiting this so that hopefully now you can get a deeper understanding of what it means and use it as you move forward. Now, you might say, why are we deriving these, Professor Saad? Why are you doing all this math? Okay, for a few reasons. First, as graduate students, I want to make sure that I give you something as rigorous as possible. So to prove to you that this is what the Reynolds-Strasberg theorem does, we have to derive it. Second, while you might not ever do a derivation later in your career, being exposed to it is important. Because as grad students, you are, as grad practitioners, you're gonna be expected to create things, to create new ideas and new concepts. And having in your tool belt, having been exposed to how to do derivations and these complex things is gonna help you in the future, okay? If it doesn't, maybe email me like in 15 years. If it does, also email me, okay? All right. So now we're gonna derive the Reynolds-Strasberg theorem, derivation of RTT, and I'm going to use mass conservation to do that because it's a very simple concept to understand. Mass conservation using mass conservation. Okay. So I'm going to take a fluid flow. Imagine there's fluid flow over here. And I'm going to consider a just arbitrarily shaped control volume. For simplicity, we're going to take it nice shape like this. Okay. I'm going to call this my control volume. Now, really, this control volume is three-dimensional. Okay. So don't forget that. I'm only showing, so you can assume unit depth if you want. Okay. Okay. So each one of those faces is called the control surface, right? Each one of those the surfaces are what constitutes the control surface of the control volume. So control volume is CV. These guys are control surfaces. Okay. Now, for simplicity also, doesn't matter in the end, all of these things have been worked out. Consider a system. Okay, so control volume is a region fixed in space. Many systems are going to go through it, right? Different shapes, different structures, different content. They're going to flow through this control volume. For the sake of simplicity, suppose that there is a system, okay, such that when it flows through that control volume, it takes the same shape. This just really simplifies the mathematics a lot. Okay? So what I'm drawing here in black is the control system, is the system. I want to call it control system, but it is just the system, and just so happens to coincide with the volume. Okay? Yeah. Okay. Showing in black is the system. Okay? Suppose that at the inlet over here, in space, there is a velocity, constant velocity across the entire inlet over here, U1, and a constant density U1, uniform density, sorry. And suppose at the outlet, there is a velocity U2 and a density U2. Okay. The mass of the control volume, which is equal to the mass of the system, because we said they coincide, is simply the integral of rho dv, correct? Over the control volume. So you'll notice that I sometimes I use triple integral or double integral or just one integral, doesn't matter, as long as you know what you're integrating over, volume or surface, okay? I simply just use a single integral and indicate whether it's a volume or a surface or a line. Okay? Now suppose that, say this has been observed at time t. Okay, now suppose in a time increment, delta t, that this system has moved through the control volume. Remember, the control volume is fixed, is non-deforming, it's non-changing, it's a fixed region in space. It always looks like this. But the system, that black surface, is moving. Okay? In a very small time increment, okay, the boundary of that system is going to move according to U1 and U2, right? Because U1 is going to push it just a little bit, and U2 is going to push it just a little bit. Remember, this is a very small time increment. So we're going to exaggerate things a little bit here. Okay, this is my control volume. And in this little time increment, the system moved this much. So in this, on this end, it moved a distance delta L1, and on that end, it moved by a distance delta L2. Yeah. Can you tell me what that distance is? Remember, over here you have U1, and over here you have U2. These velocities are pushing the control system, correct? So what is distance L1, delta L1? Sorry, U? Okay, so U, which U? U1. U1, yes. Length is speed times time, right? So meters per second times second. So in a small increment delta t, the surface just moved by U1 times delta t. What about delta L2? With U2, yes. It's U2 times delta t. Okay? All right, so keep those in mind. Now we're going to apply the conservation law. dm cis by dt is defined as the limit as delta t approaches 0. That's standard derivative definition, right? Standard definition of a derivative. All right, so how can we took this in t plus delta t. What is the rate of change? How can we define the rate of change as the limit? How can we define this derivative?
The system with the change minus the original.
Right. So what Arti is saying is that this derivative is really approximate as the limit, well, it's equal to the limit as delta t approaches 0 of this M system minus that M system over the time increment, right? Just rise over run. Okay. So M cis at t plus delta t minus M cis at t over delta t. Agree? Yeah. F of x plus h minus f of x over h. Okay. Okay. Now all we have to do is fill in the blanks. What is M cis at t? Why? What if rho changes inside here? Right, what about this? Yeah. So msys at t is mcv at t, which is equal to the integral of rho dv. Okay? All over the control one. Okay? Now, we're going to take a little bit more space, so we need some more space. So msys at t, we know that delta t is just a quantity that's going to shift to 0. Now msys at t plus delta t, msys at t plus delta t. Now you're going to say, well, msys at t plus delta t should be equal to msys at t. That doesn't, yeah, but that's not going to help us do anything because now we need to relate the mass in the system to the mass in the control volume. So I want you to think about expressing this just looking geometrically. The mass is going to be related to the volume, right? In this case, we're assuming unit depth, so it's really related to these areas. So msys at t plus delta t is this guy, correct? Now try to geometrically describe this shaded area in terms of the blue control volume, in terms of this, in terms of this region, delta L2. So what about saying that this msys of t plus delta t is really m of the control volume at t plus delta t minus this mass over here. We're going to call this m1, okay? Plus the mass in this region over here, which is m2. We're going to call that m2. Do you agree? It's the mass and the control volume, but I kept that at t plus delta t because we don't know if the mass changed in the control volume or not. I'm going to allow it to change, so I'm going to write it mcv at t plus delta t. Remember, the mass and the control volume might change, only the mass in the system is not going to change, but the mass and the control volume might change. That's what we're after. So just by inspection, it's the mass of the system at t plus delta t, because it won't just hold it, it's going to be equal to the mass in the control volume minus the mass that kind of left, plus the mass that, well, yeah, plus the mass in this region over here, right? Just by inspection. Okay? Any dissenting points of view over here? Okay. All right. This guy, it is what it is. It's mcvt plus delta t, and I have from this term, I have an mcvt. So what I'm going to do later, I'm going to get a derivative from mcvt plus delta t and mcvt. So I'm going to leave this term as is. But what we can manipulate, what we can play with, is m1 and m2. So help me find m1. You have all the ingredients. What is m1? Now remember, this has a surface area over here. Okay? Call the area A1 for simplicity. So what is the mass contained in this region, in this volume 1? Rho 1. Rho what? Delta L 1. Okay.
Delta L1
Uh-huh.
and A1.
A1, yes. Density times volume. Correct? So kilograms per cubic meters times meter times meter squared gives you kilograms. Now, help me know, but delta L1 is not very useful. I need to express it in terms of a primitive quantity like velocity. What is delta L1? Yep. So we get rho1, u1 delta t, a1. What about M2? Rho 2 u2 delta t a2. Okay. I don't care about a1 and a2 what they look like. Doesn't matter. You can measure that. This is a formula independent of the shape of the control volume. Okay. All right. So now msys at t plus delta t is mcv at t plus delta t. Okay. Minus what is m1? We said rho1 u1 a1 delta t plus m2, which is rho 2 u2 a2 delta t. Okay. Now we can add those together. Okay. Right, so d by dt of msys, that was our original definition, was equal to the limit as delta t approaches 0 of msys t plus delta t minus msys at t over delta t. Okay? So now let's fill in the blanks. Help me out. Limit as delta t approaches 0. Let's write everything out. So msys of t plus delta t is what? Mass of the control volume at t plus delta t minus rho 1 u1 a1 delta t plus rho 2 u2 a2 times delta t, correct? Minus mass of the control volume at t all over delta t. Okay, is this starting to ring a bell? Limit as delta t approaches 0. So mcv t plus delta t minus mcv t over delta t. I'm going to put those together. mcv at t plus delta t minus mcv at t over delta t. Okay. Now delta t in this, for these guys, it just cancels out, right? So you don't need a limit anymore. Because there's no delta t anymore in those terms. So you just drop the limit and you say minus rho 1 u1 a1 plus rho 2 u2 a2. Almost there. Okay, now, what is this? Limit of delta t approaches 0, mcv t plus delta t minus mcv over delta t. I claim that this is the derivative of the mass in the control volume over dt. Okay? Minus rho 1 u1 a1 plus rho 2 a2. Now notice here I used a partial derivative for the mass and the control volume. Because the mass and the control volume is also going to be a function of space. So that control volume can also change, the mass in it can change in space. So that's why I made sure that I have d by partial t. Okay? One more step. What is the mass and the control volume? You get d by dt of the integral of rho dv over the volume, over the control volume, minus rho 1 u1 a1 plus rho 2 u2 a2. Okay? And that is equal to 0, right? No, that's equal to 0. But in this case, what I care about is this translation from d msys by dt to partial by partial t of rho dV minus these minus plus these. Now, does this ring a bell from your undergrad fluids? Forget about this term, assume you have absolutely constant density everywhere, so, and no change in time, steady state, so this term disappears. This equation is simply telling you whatever mass is coming in is leaving. You remember that, right? See how we went from dm cis by dt equals 0, that we couldn't do anything with, to something that's actually useful. Velocities, we can deduce what the velocity is, what the speed is. Okay? We're going to come back to visit the this mass conservation law, but my objective here is to just show how we're going to build the Reynolds transport theorem. Okay? Any dissenting points of view? Okay. I hate asking, is this clear? If I ask it, please correct me. I prefer to ask if you have a dissenting point of view, if you want to challenge what we're discussing. Okay, so now we're going to take this up a notch, because my objective was to derive in general the Reynolds transport theorem that's going to apply not only to the mass conservation, but I also wanted to apply on momentum and on energy and whatever other quantity we're going to develop an equation for. Okay. I'm using the mass just simply as a segue to develop that Reynolds transport. Oh, so now I'm going to take that same control volume and say, okay, so that control volume, I'm going to speed things up a little bit here. I'm going to assume that the velocity is not necessarily aligned with the flow direction, or it's not perpendicular to the inlet surface. Okay, so suppose now that this is U1, it's a vector, and this is U2. This is U1, and also again this is the control volume. We really don't know what the velocities are, but we're going to assume that we know them so that we derive a relation between the velocity and everything else, right? So this is a control volume. And the system now, again, we assume it coincides with control volume at time t. Okay? And then in an increment delta t, same thing is going to happen. But what we care about, I know velocity here is going to push the surface up and the surface down. But what matters is, in this small time increment, and how did this surface move? Okay? So suppose that it also moved just a little bit, just like in the other case. This is really bad. Sorry about the markers. Okay. Just like in the other case, I'm kind of exaggerating things and not drawing them exactly to scale. Okay. Now, what matters over here, with respect to the control volume, I'm gonna magnify this a little bit. This is the control surface, and you have the velocity that is pointed out, pointing in this direction. Okay? What matters is the component of the velocity that is perpendicular to the control surface, because each vector has these two components, right? It's got the axial component, the vertical component. We know that the vertical component is not going to bring in any mass into the surface, right? Into the control volume. The only component of velocity that is bringing things into the control volume is the normal component. Okay? So if the unit normal over here is m1, then this component, this is u1, and this guy is u1 dot m1. Okay? right? That's the component that matters to us. So in that case, this delta L1 still has a delta L1 change, but it's no longer just U1 times delta T. It's U1 factor dot N1, so that gives you this component, okay, times delta T. Now really you should put a negative sign in this case. Okay, I'll take the absolute value to this distance. So we're not going to worry about that. Same thing over here. Delta L2 is U2 dot N2 delta T. Okay? You do the same procedure we did before. What you get is dmsys by dt, this total derivative. You still have the partial by partial t of the mass in the control volume. Okay? And then what you get is plus rho 1 u1 dot n1 n1 plus rho 2 u2 dot n2. Now notice here, there's no negative sign. The lectures on the YouTube have a little typo over there. Because u1 dot n1 is negative. So it takes care of the sign automatically. Okay? So now we went from a constant, just a constant velocity to a vector. But really, this one is just a special case of. Okay, final step. Now suppose that the velocity over here is just kind of all over the place. It's not constant, it's not in one direction, just all over the place. Same thing over here. Okay, so U1. Suppose it's just all over the place, okay? And this is at t. Now at t plus delta t, the control surface is going to be all jagged up, right? Because this velocity pushed it a little farther than that one. Okay, this is the control surface. And this velocity just kind of looks all weird, okay? Again, this is in 3 dimensions. Okay, so there's a volume over here. Okay, the volume over here, mass. Same thing over here. Surface is it's just like 3-dimensional. Right, it's a surface, crazy shape. Okay, so I want to jump now from this to an integral form. Okay. The same token, so this, we know that this thing is related to, sorry, so there's an A1 over here. Okay? My fault. There's an A1 and an A2 over here. Over here, the velocity is not constant across A1, okay? It's not constant across A1, so M1 can be written as the integral, okay, over this entire surface, okay, as a surface integral over A1. How much mass is coming in? You say this is rho 1 U1 dot N ds. Think of this as rho 1 U1 dot N ds as a differential element of mass, okay? Ever so small. Okay? And then we're summing it up over this entire region. Okay? So rather than having to define a delta L, which is hard to define over here, we went after computing the entire mass in this volume. We want to verify that this has units of mass, kilogram per meters cubed times meters per second. times meters squared. That gives you kilograms per second, which is what we need, right? Because we need dm by dt, rate of change of mass per second. Okay? I should call this m dot. Same thing over here. M2, so over A1, is the integral over A2. So this is still A2 over here. It's still that area over here. A2. But we're integrating, we're summing up the entire mass under this surface. It's rho 2 U2 dot N2 times ds. You will find that in practice, when we apply these, we're going to be dealing with kind of simple velocities or just nice, smooth flow such that this integral can be calculated. Okay. Now, in this case, when you combine M1 and M2, you don't care anymore about U1 and U2. What you care about is the velocity along the control surface. This integral is at the control surface 1, and this integral is at the control surface 2. What if you have 50 other control surfaces? All you have to do is just add them up, right? Just add up these integrals. No need to worry even about the sign, because u dot n is going to take care of whether flow is coming in or flow is leaving. So if you repeat the same procedure, what you get is dm cis by dt is, you still get the partial by partial t of the mass in the control volume, which is fixed. And then you have this beautiful integral over the control surface of the control volume, which is fixed, of rho u dot n ds. Okay, so let me repeat. This integral, you take it, if your control volume is like it's a sphere or something, ellipsoid or something weird, you have to calculate this integral at every point. But in practice, we do with our control volumes like cubes or rectangles, right? So the control surfaces are well defined. And in that case, this integral is simply the integral at control surface 1 plus integral at control surface 2 plus integral at control surface 3, and so on and so forth. Just like what you did in undergrad. Okay? So this shouldn't be new to you. Revisiting it from a more mature perspective is kind of helpful, is potentially what's new. But you probably never thought of using this to derive the equations, all the equations of fluid motion in this perspective. Okay, great. So now, I hope you agree that we were able to translate from a system description to an Eulerian description, from an Lagrangian description to an Eulerian description. Everything here has nothing to do with the system. It's all control volume. It's a region in space. This has space in it. This has time. Okay, but it describes a fixed point in space. What's happening at fixed points on the control volume. This guy just tracks the system. This is critical. We were able to translate from a system to an Eulerian. But we did it for mass. Now, if you do everything I did here, but do it for an arbitrary quantity, you're going to get the same answer. Okay? And we'll just do that. We're not going to do the entire derivation. We're just going to replace some terms in this equation so that we can apply it to any generic problem. Okay, so in fluids, we distinguish between mechanics, between extensive and intensive problems. Extensive property is a property, that depends on the system you consider. It's very unique to that system. The mass in this room, the mass of air in this room, okay? Your mass. It's very specific to you. An intensive property is independent of the entity you're dealing with. For example, the density of air at standard conditions is the same over here as it is down in Salt Lake, as it is at my home in Sandy, right? It's a property, it's an intensive property of fluid. It's a unique property of the fluid, doesn't depend on the system you're considering, okay? But there's a relation, typically, for an extensive property B, the corresponding intensive property, we could write it in lowercase, and the relation between B and B is that B is equal to the integral of lowercase b, the intensive property dm, okay, which is equal to the integral of b rho dv, because dm is a small mass element, which is rho dv. That's how you derive these quantities. So, for example, mass, let's do some examples. Mass is an extensive property. Extensive property. Its corresponding intensive property is what? Corresponding intensive property, simply 1. It's number 1. Okay? Because if you write it in this form, mass is the integral of rho dv, right? So this b is 1. Momentum. Momentum, some people call it p, is equal to m times v. Okay? So in this case, momentum is an extensive property, and the velocity is the intensive property. The b and lowercase b, the b's can be vectors, can be whatever you want, okay? Just think of it as the intensive property is the extensive property per unit mass. Okay? Here's another definition. Intensive property, intensive, is extensive per unit mass. So velocity is momentum per unit mass, for example. Okay? Now, with this in mind, the Reynolds transport theorem is then written as so from now on, we're just going to take it and apply it, but RTT, Reynolds transport theorem, says that the rate of change of an extensive property on a system is equal to the partial rate of change on the control volume, really any control volume, of rho times the intensive property dv plus the integral of the control surface of the same control volume, so these are related, rho b u dot n ds. So compare that to the formula we just derived for mass, where our extensive property was mass, the intensive property was 1. Yeah? Think of this term as the rate of change of rho times the intensive property, or something related to the extensive property inside the control volume, plus the flux, the net flux of this property into and out of the control volume. The way to think of this integral, again as flux, think of U as the mechanism that transports things in a fluid. It's called advection, convection, you've heard of that. It all comes from this. In a fluid, The velocity acts as a very strong mediator of information. Information can be pressure, temperature, etc. So B times U is telling you you're transporting B or rho B with the velocity U. You dot it with N, it tells you, whether you're coming in or leaving, right? Depending on the sign and on the surface. And you take the integral, you sum it up over all the control surfaces. So what this is saying, what the Reynolds transport theorem is saying, the change of a system inside the system, you translate to the control volume, and it has to do with the local rate of change in the control volume of everything related to that property, or think of mass again, plus the net flux in and out. And those should balance. So everything that's coming out minus everything that's coming in, plus the local rate of change, that expresses this conservation law, all of the conservation laws, and that's equal to the rate of change of this property of the system. So our next step is going to be, we're going to take all of the laws that we wrote, we're going to apply this to them. For mass, we already did it. B was equal to 1. For momentum, B is going to be equal to U. All we have to do is just plug it in here. That gives us an Eulerian description of this system description. Then we will do mass conservation next. We will spend a few lectures on mass conservation, revisit everything. Then we're going to start looking at momentum. Remember, with momentum, this is one side of the story, dE by dt, converting it this way, but we have the right-hand side of momentum, which we still don't know what it looks like. We said there's gravity, there's pressure, and viscous forces. We don't know a lot about those, okay? So those are going to be the next steps in the semester. For every law we apply, we're going to do some examples, we're going to understand the meaning of incompressibility and challenge some pre-existing ideas, the meaning of viscous transport, and so on and so forth, okay? Okay. Have a nice long weekend. I'll see you on Wednesday, right? And revisit the lectures on YouTube, the permanent lectures on YouTube, okay? It does this very nicely.